and we have discussed the generator characteristics regarding this open circuit characteristics, short circuit characteristics, zero power factor characteristics. And then we are discussing calculation through calculation of that voltage regulation through MMM method. MMM method. Do you remember this? I think we were here. Do you remember this? Hello? 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 Am I audible to you? Do you remember that? I think we were here when we last had the class. মনে পড়ছে? Yes or no? Maybe some set of persons attending some classes, you may be the other set. Did you attend the other classes, earlier classes in this subject? Rahul Das, I remember your name. I think you were there. So we were discussing the voltage regulation, if you remember. And then we discussed the EMF method, right? And then we came to MMM method, and from there we got to know different generator characteristics. We needed to know rather. Then we started discussing generator characteristics, and then these are the after the ZPFC, zero power factor. So these are the steps actually through which we can calculate voltage regulation through MMM method, magnetomotive force method, MMM. Okay. So now here see that the equivalent circuit, if you remember what we discussed, it's looking like this. So this is the terminal voltage per phase, and then this is armature resistance, this is reactance, and this is node EMF. So now if you see this phasor diagram, so there is a intermediate phasor E0 dashed, which can be calculated by doing VT plus IARA, VT plus IARA, interim voltage, interim EMF, E0 dashed. So after taking the resistive into account, okay. So then if you draw the phasor diagram, this is VT plus IARA will be E0. Right side, there is a phasor diagram. And the phase of E0 dashed is having delta dashed, lagging with respect to VT. Because we have assumed here always lagging load, right? We have assumed here lagging load. So now corresponding to E0 dashed, there will be one FF dashed from OCC, right side below, you see there is a OCC drawn, and corresponding to E0 dashed, you can find out FF dashed. কিছু মনে পড়ছে? কন্টিনিউটি হারালে তোমরা পড়েছিলে পুজোর ছুটিতে বা কোথাও? কোন তো আর্জি দেখলাম না যে ক্লাসগুলো একটু করি স্যারকে বলে। তোমরা তো বড় হয়ে যাবো, ঠেলে ঠেলে কত করাবো বলো? So E0 dashed corresponding to this, you have MMF FF dashed. কোন রেসপাচা শুনতে পাচ্ছ তো? Okay. All right. So now it is written also, find E0 dashed from 1. So you can calculate E0 dashed because you know what is armature current, what is armature resistance, and what is the terminal voltage. So from that you can calculate E0 dashed. Now step 2, find FF dashed corresponding from OCC. So OCC is drawn here. So now phase of E0 dash, it is clearly shown. It is actually when the current is lagging by angle theta. So you have assumed, we have assumed lagging load, lagging power factor load. So we have E0 dash is having a phasor of pi by 2 minus delta dash, E0 dash, sorry, minus delta dash. And if you see that behind this E0 dash, FF dash, which will be leading E0 dash by 90 degree. So the phasor of FF dash will be actually 90 degree minus delta dash from reference phasor VT. It's quite clear. So then you have measured or you have got the value of FF dash from OCC and you have known phase also. Now in step 3, you have two short circuit characteristics. So now short circuit characteristics is what? Actually, it is actually IA versus E0. IA versus 0. Just a minute, someone is. Right. So it is IA versus E0. Now we go to so IA versus IF. So IF is proportional. IF is having E0 also. So you can say IA versus IF. Right. So IF and E0, they're related. If you give a field, right, so you can have no load EMF also, right? So actually, you can draw IA versus IF, IA versus E0, anything, but for this calculation, we will use IA versus IF. Now you come to this. This. So IA versus IF, or on the other hand, you can use IA versus FF, the field MMF, right? The field MMF, IA versus field MMF. So now corresponding to that IA, you can calculate the armature MMF required, FA, right? Now FA plus FF dash, FA plus FF dash is final FF, right? FA plus, sorry, FF plus FA is FF dash. Now you can get FF equal to FF dash minus FA. Are you getting me? These are this is the basic formula. The field MMF armature MMF will give you the resultant phasor. Now here your resultant phasor is FF dash, which you have found out from corresponding. So now then you know FF dash and you know FA from short circuit characteristics. So you can calculate the no load MMF, FF. FF dash minus FA is actually FF from this equation. Just a minute. So now, if you know this, so you can FF dash. I told the magnitude is known pi by 2 minus delta, and FA armature magnitude is known from short circuit characteristics, and phase is actually the armature current phase. The phasor location is the same as the armature current. So now if you make minus FA, from the plot it is minus FA is the opposite direction. So FF dash minus FA. So you got FA. Now once you have found out FF, so from the OCC corresponding to FF, you can easily calculate E0. Now once you know E0, you know B, so you can directly calculate the voltage regulation from that formula, E0 minus B by E0 into 100%. So these are the steps that you can use to find the regulation through MMF method. Now here the advantage is that actually according to the load, load factor is taken care of, rather. In EMF method, we use the synchronous reactance that was calculated based on the rated values. Rated values means rated current, rated field, etc., etc. But usually in operating conditions, different operating conditions, this does not hold good. So therefore, the errors are incurred in the earlier method, the EMF method. Now to reduce that error, so we have to use different characteristics of the machine to get the actual situation during calculation. So that is why I say if your IA changes, naturally FA will change. So naturally you get a different value of FA, right? So here you get a better accuracy. Accuracy is improved, you can say, and improved to a good extent. Error is much lesser compared to what we find in this EMF method. The third method is actually zero power factor method. Zero power factor method, Portier, or sometimes it is known as Portier triangle method. Okay, so this method requires both OCC and ZPFC for calculation. OCC and ZPFC. So now you see that here in the first step, what we do, we draw Portier triangle first. Now, what is a Portier triangle? That I will tell you. Now, step one, the prerequisites are written here. That armature resistance, terminal voltage, armature current, and power factor angle are known from the given data. Naturally, what you know, the armature resistance is mentioned. If it is not mentioned, you can assume it to be zero. No problem. Now, if it is mentioned, then you know it, right? A terminal voltage, at which voltage the machine is operating, and at which load, that means the magnitude of armature current and power factor, you have to calculate the voltage regulation. That is also known. Okay. And here you should require to know the OCC and ZPFC data. OCC and ZPFC. In the other case, that is the MM, we used to have, or we used to know the data of OCC and SCC, short circuit characteristics. But here you must know the data of OCC and zero power factor characteristics. Now, you know OCC and ZPFC, so you can draw these two characteristics, OCC and ZPFC, right? So now from there, you can draw Portier triangle. Now, what is Portier triangle? It is behind the name of scientist Portier. Now, what he did some work empirically, and the work is like this. So now, you just understand first what is Portier triangle. So now, when we explain the term, ZPFC, rather ZPF characteristics, zero power factor characteristics, we saw the plot, the kind of plot what is shown in the this figure, right? From A, and it is having the shape which is absolutely almost nearly similar to OCC. It is like a shifted OCC. So now from the origin O, the MMF axis OA, right? OA MMF is the MMF what we called that time while drawing that characteristics is minimum MMF required to develop some voltage, right? Or rather, it is the MMF required to overcome the armature reaction effect and the leakage reactance effect, considering totally zero power factor load. That means zero power factor lagging load, totally inductive load, right? So now see, so many persons are entering late. So now you see that this zero power factor characteristics, and the y-axis we have the voltage, right? And from the rated voltage, if you draw a line horizontal, parallel to the field axis, rather you can say. So these lines cuts both the OCCs and ZPFCs at some points. Now with ZPFC, it crosses at the point B, right? The horizontal line drawn from V rated. So now from B, right? Now another thing is that which I told while drawing that OCC. The OCC has quite a bit of linear portion, right? Due to the air gap present in the magnetic circuit. So now if you draw a line which is actually tangent to this linear portion, right? So you get a line which is known as air gap line, right? Air gap line. So now from the point B, see, you can cut section BC, which is equal to OA. BC equal to OA, you can cut, okay? Now from C, if you draw a line parallel to the air gap line, it will meet the OCC at point D. So now the triangle BCD, if you add, if you add BD, so you get a triangle BCD. So this triangle is known as Portier triangle. Now from D, if you draw perpendicular on BC, it is DE, right? So you get a line DE, line section DE, right? This DE represents some voltage because it is parallel to the voltage axis. Now this voltage, it has been observed that it is a voltage drop across the armature leakage reactance. IAXAL drop, right? DE is the
স্যার
IAXAL drop. হ্যাঁ
স্যার স্যার বলছি আপনার
হ্যাঁ বলো।
স্ক্রিনটা না দেখা যাচ্ছে না, মানে ব্ল্যাঙ্ক দেখাচ্ছে।
এই রে এতবার আমি সুইচ করছি বলে হয়তো হচ্ছে, কারণ সবসময় এখনো এন্ট্রি হচ্ছে তো দেখছি আমি যদি কতক্ষণ ধরে হচ্ছে এটা
এই স্যার ২-৩
এক্ষুনি
মিনিট
হলো।
ধরে এরকম দেখাচ্ছে। হ্যাঁ ২-৩ মিনিট ধরে দেখাচ্ছে।
আচ্ছা 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 ঠিক আছে, আমি এটা দিচ্ছি, দেখি। দেখো তো এবার পাচ্ছ কিনা, তোমরা পেলে তো আমি স্টার্ট করবো।
হ্যাঁ স্যার এবার ঠিক আছে, এবার ঠিক আছে।
ঠিক আছে,
হ্যাঁ
আমি আরেকবার কি প্রক্রিয়াটা দেবো, না
ওকে
এখান থেকে
স্যার,
দেখে বুঝতে পারছো?
ওকে।
বুঝে গেছো তো?
হ্যাঁ স্যার, হ্যাঁ স্যার।
অ্যাকচুয়ালি এয়ার গ্যাপ লাইন ড্র করা হয়েছে, দেখতে পাচ্ছ এয়ার গ্যাপ লাইন। হ্যাঁ এখানে লেখা আছে। তারপরে বিসি ইজ ইকুয়াল টু এ, বি হচ্ছে ভি রেটেড থেকে প্যারালাল লাইন টানা হয়েছে with x axis, that is the filter axis, right? Now from C you draw a line which is parallel to the air gap line, it meets OCC at point D, so the triangle BCD is known as Portier triangle. ঠিক আছে? Now if you draw a line perpendicular from D on BC, that is DE, so this line DE represents some voltage because it is parallel to the voltage axis. Now this voltage is actually the leakage reactance drop of the machine. Leakage reactance drop, right? Now here the first step is to draw the Portier triangle first, and then you can calculate the leakage reactance because DE is IAXL. So now you know IA, magnitude of IA. So therefore XAL you can find out at that point. So DE by IA, DE by IA, XAL, right? So then armature leakage reactance you have found out. And in step 2, you can redraw the equivalent circuit. And here the interim voltage, instead of just having RA drop, you can have RA plus JXAL drop, and you can have that interim EMF E0 dash, because you have already calculated XAL based on the armature current which is given in the problem or which is known to you, right? So then actually from here you can calculate E0 dash, that is actually V plus IA into RA plus JXAL. দেখতে পাচ্ছ তো স্ক্রিন? আমি অনেকবার আবার এন্ট্রি হচ্ছে বলে আমাকে চেঞ্জ করতে হচ্ছে, ভেরি সরি, কিন্তু এখনো দেখা যাচ্ছে তো? তো এবারে দেখো ফেজার ডায়াগ্রাম আছে। So VT plus IRA plus JIXL is E0 dash. All the time they're entering, I don't know. It is 3:30, still entering. Okay, anyway.
আচ্ছা স্যার, আমাদের কিন্তু এই ক্লাসটা যে এখন হবে এটার কোনো নোটিশ ছিল না।
আমিও
আমাদের
জানি,
জাস্ট
বুঝতে পেরেছি। আমি
5
কালকে
মিনিট আগে
বলেছিলাম 3টের
এরকম,
সময়। হ্যাঁ বলো।
5 মিনিট আগে এরকম নোটিশ যদি দিয়ে যদি ক্লাস হয় তাহলে মানে এরকম আধ ঘন্টার পরেও লোকজন এন্টার করছে, এটা হবেই, এটা এক্সপেক্টেড, এটা কিছু করার নেই আপনার।
বুঝতে পারছি। নয়, এটা নোটিশটা আমি কালকে বলেছিলাম, কেউ একজন ফোন করেছিল আমাকে, হ্যাঁ তাকে আমি বলেছিলাম তো যে আজ 3টের সময় ক্লাস করবো। হয়েছে কি এটা কথাটা দেরি হয়েছে, হ্যাঁ সেটা ঠিকই, লিঙ্কটা ঠিক আছে। আমি কালকে কিন্তু বলেছিলাম আজকে 3টের সময় ক্লাস হবে, বুঝছো? ঠিক আছে, এনিওয়ে। So in step 2, you just see that you have VT IRA plus JIXL E0 dash. It's step 2. So if you consider a lagging load, right? So your E0 dash will be leading, that is at angle delta dash. So now in the next step, so you can draw the phasor diagram, MMF phasor diagram also. That is that corresponding to E0 dash, you can draw a dash which is leading E0 dash by 90 degree, right? So now FF dash phasor FF dash 90 degree plus delta dash, right? So FF dash phasor will be having an angle of 90 degree plus delta dash with respect to dt. ঠিক আছে? দেখা যাচ্ছে স্ক্রিন? হ্যালো?
No, sir.
আরে কোথাও দেখা যাচ্ছে কোথাও দেখা যাচ্ছে না, এরকম তো হবে না। দেখো পাচ্ছ?
No, sir.
সে আবার কি?
হ্যাঁ
জাস্ট
স্যার,
মিনিট
দেখা
দাঁড়াও।
যাচ্ছে তো।
দেখা গেলে সবারই দেখা যাবে, আর দেখা না গেলে কারোরই যাবে না। এরকম তো হবে না যে কেউ দেখতে পাবে কেউ দেখতে পাবে না। দেখো
হ্যাঁ দেখা যাচ্ছে।
তাহলে এবার এফএফ ড্যাশ যদি পেয়ে যাও, এফএফ ড্যাশ যদি পেয়ে যাও, তো করেসপন্ডিং টু ওসিসি ইউ ক্যান ক্যালকুলেট E0 ড্যাশ। ওসিসিও তোমার জানা আছে, বলেছিলাম প্রিরিকুইজিট হচ্ছে ইউ মাস্ট নো ওসিসি এন্ড জিরো পাওয়ার ফ্যাক্টর ক্যারেক্টারিস্টিক্স। নাও E0 ড্যাশ যদি জেনে যাও করেসপন্ডিং টু এফএফ ড্যাশ, রাইট? E0 ড্যাশ যদি সরি এফএফ ড্যাশ যদি জেনে যাও করেসপন্ডিং টু E0 ড্যাশ, its phasor is known, then you can apply the same formula, right? Your FF dash to your resultant, and then FF plus FA equal to FF dash. Now here FA is actually BE. এবারে আরেকটা জিনিস দেখাই, ডায়াগ্রামটায় পোর্টিয়ার ডায়াগ্রামে। এবারে দেখো এই যে পোর্টিয়ার ট্রায়াঙ্গেলটা, ডি সিগনিফিকেন্সটা বললাম, ডি ইজ দ্য IAXL drop. But you see, if you consider this horizontal line BC, or rather BE, CE, etc., these are on MMF axis because they are parallel to MMF, right? Now, out of which CE will represent the MMF corresponding to the leakage reactance, right? And BE will actually represent the MMF corresponding to armature reaction, right? So now here the effect of the reactance has already been considered because you have calculated E0 based on your RA and XAL, right? So the only remaining part is BE. BE is the armature reaction effect. So now you have to consider the MMF divided for armature reaction, which is BE here, which is BE here. So then you have got in the next page, say FF plus BE equal to best, and step 5 you get that FF equal to FF dash minus BE. So now here you get the phasor of BE, same method of current, that is minus theta. So you can just calculate your FF, that the final or rather no load MMF. And from FF again using OCC you can calculate the no load EMF. Now once you know no load EMF, you can calculate the voltage regulation based on the known formula E0 minus VT by E0. Okay. These are the major three techniques that are used for calculating the armature you can say voltage regulation, armature voltage regulation. But actually there are other methods also. Now ASA method, it is consult your books or I can explain. It's similar, but it considers some saturation effect. All. So I think if you don't understand it, I can discuss here. Otherwise, to cut short the thing, this is enough actually. After this Portier triangle method, this is fairly accurate. This Portier triangle method. I mean, here you can accurately calculate the leakage reactance effect, and then the armature reaction effect, and then calculate the voltage regulation to a high accuracy, to a very high accuracy, you can say. So this method is actually that American Standard Association method. So it also uses say empirical formulas or empirical assumptions. Now, for that, I think you just go through first the book. If you don't understand, in the next class, I will just tell you. eh? Because then at least up to power thing, I should explain power angle characteristics. The next step is actually how to determine parameters. Now, if you circuit, right? You know, induction machine also, DC machine also, equivalent circuit parameters. So here also we have equivalent circuit parameters, and in the equivalent circuit we have seen there are two elements mainly. One is XS and another is RA. Armature resistance, and XS is synchronous reactance, right? So now out of these two, RA is quite insignificant, as I was telling repeatedly, because the ratio of XS to RA is very, very large, and while calculating the voltage regulation and all, the effect of RA does not matter much. XS is the major factor. So XS determination is actually our major concern. Otherwise, to determine armature resistance is very easy. You can use any standard low resistance or very low resistance measurement method, maybe Kelvin double gauge, etc., and then multiply these values obtained by this Kelvin double gauge with some factor, because there you use DC supply and the machine is actually used under AC, right? And there are skin effects, and which can because of higher diameter of the conductors, okay, so the skin effect can become significant. So you can at least multiply by the obtained value by 1.5 to 1.6 even, to get the, it depends on machine to machine. Smaller machines, the multiplication factor is lower. For larger machines, the multiplication factor will be higher, because you have larger diameter conductors with larger diameter for bigger machines. So that's all. Now, excess determination, there is a synchronous reactance. Use short circuit test. We use short circuit test. What is short circuit test? You short circuit the armature and run the machine at a speed between 1/3 of synchronous speed to any synchronous speed of near or even higher. And then you measure you apply some field current, rather field voltage, right? Voltage at the field. So there is a field current, okay? And then you measure the short circuit current, okay? Now the division of E0, right? Division of E0 by say this IASC, short circuit voltage, will give you, short circuit current will give you the measurement of XS. So that has been already known. Still repetition I'm doing here. This, so IASC is actually E by square root under, you're looking at the equivalent circuit, RA square plus XS square, right? So now from SCC, you can have IF. You give actually field current. Corresponding to that, you have to calculate, know what is the EMF. That is from open circuit characteristics. Okay, you can use open circuit characteristics data, and then you determine E0, and then E0 by that short circuit current will give you the measurement of XS. E0 by the short circuit current, the last XS E0 by IASC magnitude. So you can calculate XS to a very fairly accurate value, at a fairly accurate value. So now you see, power angle characteristics. The other term what we will discuss now is the power angle characteristics. Now, what is power angle? Now, if you look at the diagram, what I was drawing earlier, so there is a between E0 and VT, right? E0 and VT. Okay. Now, if you calculate the power, you will find that this actually plays a significant role for power or power delivery from the machine to the load or to the grid. So therefore, this angle is known as power angle. Angle means the angle between E0 and T. So now here, this screen visible. Hello. Here you see that we always assume that the terminal voltage is a reference value with the reference phasor of 0°. So now E0 is having some angle, right? E0 is having some angle. So now I don't know whether you have read the power flow equation or not. So if you find that E0 is leading Vt by some angle, that is the delta which is shown here. The power flows from the machine to the load. That actually machine acts as a generator, right? And if E0 is lagging, right, from Vt, right, delta is minus delta, right? So power will flow from Vt towards the E0, that means towards the machine. That means the machine will work as motor, right? So then while motoring, we will consider delta to be negative, and while generating, we will consider delta to be positive. This is the reason what we will follow throughout. Okay. So now considering that it is a generator, so you can apply Kirchhoff's voltage law in the circuit given. So you can know what is the value of Vt. Vt is actually E0 minus Ia into Ra plus Jxs. So now from which you can calculate Ia, which is actually E0 minus E0 angle delta minus Vt angle 0° by Zs. So Ra plus Jxs, this has been already known that it is Zs at an angle theta s, right? So this is E0 minus Vt by Zs. So then power at load actually can calculate like this: Vt into Ia conjugate, phasor Vt Ia conjugate, right? You have seen from your first year how to calculate power having known Vt and Ia. Vt Ia conjugate, or also you can do Vt conjugate Ia, whatever it is. But the thing is that if you take Vt conjugate Ia, that reactive power will be negative, convention will be just a little different, but you can magnitude same value. Now, Vt into Ia conjugate, if you take, so Ia is here. Ia conjugate is nothing but E minus delta minus Vt 0. 0 plus 0 minus 0 is same. So you have Zs minus theta s. Now, if you multiply both of them, so you get E0 Vt by Zs angle theta s minus delta and minus Vt square by Zs theta s. So this is the complex expression for total power, right? So now you can split it up into real and imaginary part, giving rise to active and reactive power. So if you see, if you split it up into real and imaginary part, so you can get P plus JQ equal to, so E0 Vt by Zs cos theta s minus delta minus Vt square by Zs cos theta s plus J E0 Vt by Zs sin theta s minus delta minus Vt square by Zs sin theta s. That's quite clear. So now, just by seeing it, you can see that P is the real part and Q is the imaginary part. Now, if you take the active power P, so this gives you the first part, that is E0 Vt by Zs cos theta s minus delta minus Vt square by Zs cos theta s. Now, from here, you can do a little bit of, say, trigonometric adjustment with the help of the impedance triangle. Now here impedance triangle is drawn at the left, okay, where Ra x theta s is the angle, and then Zs and alpha s. Alpha s plus theta s is 90°, right? From the impedance triangle, right triangle you can see. Now from here you can see alpha is equal to pi by 2 minus theta s, or theta is equal to pi by 2 minus alpha s, whatever it is, okay. So now if you theta s here, in the first term of P, you get E0 Vt by Zs cos pi by 2 minus alpha s minus delta. So then right term is same, cos theta s. So now from here you can rewrite this like this: the E0 Vt by Zs sin delta plus alpha s minus Vt square by Zs. Now cos theta s also from the impedance triangle you can write as Ra by Zs. Cos theta s is Ra by Zs. If you replace it, so you get minus Vt square Ra by Zs square. Okay, this term you get. Now from here you can have two cases. Now always I was telling that for a better approximation or for easier calculation, you can sometimes take like Ra equal to 0, Ra negligible. Now if you do that, then your xs will be actually Zs and alpha s will be 0, because Ra you have neglected, Ra is 0. Now, putting that, R equal to 0, and then alpha is equal to 0, you get the power expression as E0 Vt by Xs. It will be Zs I have written, it will be actually Xs, E0 Vt by Xs sine delta, right? And if you draw P delta curve, so it will be simply sine curve. So now for positive delta, you get the generating portion, and for negative delta, you get the motoring portion, right? And the maximum power you can get as by calculating dp d delta equal to 0. So you get E0 Vt by Zs cos delta 0. So now that happens at delta equal to pi by 2, because E0 Vt by Zs are finite values. So only at delta pi by 2 cos delta will be 0. So you will get maximum power at delta equal to pi by 2, that is E0 Vt by Zs. So this is the same derivation, and this is the same plot and all that is shown here. So now if you include resistance, say armature resistance, if you include armature resistance, এই তোমাদের কি বুঝতে অসুবিধা হচ্ছে? আমি একটু তাড়াতাড়ি বলছি। হ্যালো, শুনতে পাচ্ছ?
না, হ্যাঁ স্যার, ঠিক আছে।
ঠিক আছে তো, বুঝতে পারছো?
হ্যাঁ।
So now actually for the case where we consider resistance, actually this Vt square by G square Ra represents some losses, resistance losses, resistive losses. So now if you have it, actually the entire expression, so you can plot P versus delta like this, and with two parts. One is P1, which is a sinusoidal variation, and another is constant term P2. P is minus P square by Zs square Ra. That is the negative half of power. Okay, this one. No, the other one actually, if you see that at delta equal to 0, right? At delta equal to 0, so you will get this whole plot. So actually, you get a term delta leading by alpha s. I mean this which one? P1. See, one plot is shown P1, right? P1. P1, the top one, P1, right? So P1 is the plot for first term, right? So now if you add both them, you will get the resultant plot. P1 plus P2 at different deltas, right? To add both of them, you get the resultant plot. Now to have an idea, you can, if you have some idea, you can see how the plot can be looking like, making by considering the case at delta equal to 0. By considering the case at delta equal to 0. Now, if you put delta equal to 0, let us say, you get E0 Vt by Zs sine alpha s minus G square by Zs square Ra, the resultant plot, right? So now this at delta equal to E0 Vt by Zs square Ra minus Vt square by Zs square Ra. So now if you take Vt square by Zs square Ra common, you get E0 minus Vt. This into E0 minus Vt. So now there can be three cases like that, that you can excite the machine in such a way that E0 equal to Vt. That is known as normal excitation. That is known as normal excitation. E0 equal to Vt. So in that case, the plot, the resultant plot will pass through the origin, right? So that has been shown in the third plot from top, right? E0 equal to Vt, third one. E0 and Vt, that is known as overexcited condition. Excitation is more than the terminal voltage, overexcited condition. So you get a resistant at delta equal to 0, and the plot is the second plot, which is shown also by arrow, E0 greater than Vt, right? And if it is under excited, that means E0 is less than Vt. So at delta equal to 0, you can get a plot which is negative, that which is by by arrow, E0 minus B, under excited case, right? So you can have these three options as the resultant, or P1 and P2 with P1 and P2 separately plotted like this. So this is what, and then হ্যালো, হ্যাঁ শুনতে পাচ্ছ? কতক্ষণ শোনা যায়নি? এই পাতাটা? ওফ! এরকম হতে থাকলে তো বিপদ। এই হচ্ছে এখন একটু সহ্য করতে হবে তোমাদের, আর কি করা যায়? দাঁড়াও ১ মিনিট দেখি। ব্যাস, বেরোতে হবে মনে হচ্ছে আবার। দেখো তো, এবার পাচ্ছ?
No, sir.
না?
No, sir. No.
উফ! দাঁড়াও, আমি আবার বেরিয়ে গিয়ে আবার ঢুকছি। হ্যাঁ, শুনতে পাচ্ছ?
স্যার শোনা যাচ্ছে, দেখা যাচ্ছে না কিছু।
দাঁড়াও, আমি এখনো তো দেখাইনি। শুনতে পাচ্ছ কিনা আমি একটা স্টেপ দেখছি।
ওকে স্যার।
এবার দেখো, দেখতে পাচ্ছ কিনা বলো। পাচ্ছ?
না স্যার, কিছু দেখাচ্ছে না তো।
তাহলে একটা কাজ করো, আজকে আমার দ্বারা নেটওয়ার্কে আবার প্রবলেম হয়ে গেল মানে।
স্যার এবার দেখা যাচ্ছে।
যাচ্ছে?
হ্যাঁ হ্যাঁ স্যার।
আচ্ছা, এই পাতাটা আমি বলেছি তোমাদের যে কিউ কি করে ক্যালকুলেট করবে। কিউ হচ্ছে ওই ইকুয়েশনটা থেকেই, মাস্টার ইকুয়েশন, ইজিরো ভিটি বাই জেড এস সাইন থিটা এস মাইনাস ডেল্টা মাইনাস বিটি স্কোয়ার বাই জেড এস সাইন থিটা এস। ঠিক আছে? এবারে থিটা ইকুয়াল টু পাই বাই টু মাইনাস আলফা এস, ইন দ্য সেম ওয়ে উই আর রিপ্লেসিং সাইন থিটা এস ইজ এক্স এস বাই জেড এস। সেখান থেকে তাহলে কিউ পেয়ে যাব। হ্যাঁ, কিউ। Then first case is actually r equal to 0, alpha is equal to 0, x is equal to js, and if you put that in the equation shown under box, it will be q equal to euro vt by xs cos delta minus vt square by xs. ঠিক আছে? নেক্সট পেজ দেখা যাচ্ছে? হ্যালো, হ্যালো, হ্যালো।
হ্যালো,
হ্যাঁ, তোমরা শুনতে পাচ্ছ কিছু? হ্যালো, হ্যালো।
হ্যাঁ স্যার, এখন শোনা যাচ্ছে।
এই তো খুব মুশকিল হচ্ছে, মানে অধ্যায় হচ্ছে না। স্লাইডটা দেখতে পাচ্ছ? কি
না
গো?
স্যার, এবার দেখা যাচ্ছে।
আচ্ছা, আজ এইটুকুই আজকে দেখাবো। এটা রিয়াক্টিভ পাওয়ার যদি দেখো, E0 VT বাই এক্সএস কস ডেল্টা মাইনাস ভিজি স্কোয়ার বাই এক্সএস। হ্যাঁ, তার দুটো টার্ম হলো Q1 আর Q2। Q2 হচ্ছে কনস্ট্যান্ট, দ্যাট ইজ মাইনাস ভিটি স্কোয়ার বাই এক্সএস। আমরা এই যে অ্যাক্সিস থেকে নিচের দিকে আছে দেখো, মাইনাস ভিটি স্কোয়ার বাই এক্সএস, দ্যাট ইজ Q2। হ্যাঁ, এই যে অ্যারো দিয়ে ডান দিকে দেখানো আছে, দিস ওয়ান কনস্ট্যান্ট টার্মটা। এবার ফার্স্ট যে টার্ম E0 VT বাই এক্সএস, দ্যাট ইজ এ কোসাইন টার্ম কস ডেল্টা। তার মানে ইটস ভ্যারিয়েবল উইল বি অ্যাজ পার লাইক দ্য কার্ভ। যদি হয় তাহলে ইউ উইল গেট যে যে টপ কার্ভটা E0 VT বাই এক্সএস কস ডেল্টা এইভাবে দেখানো যায়। এবার তার সঙ্গে যদি ফাইনাল Q1 প্লাস Q2 করো, দ্যাট ইজ অ্যাকচুয়ালি addition of this two, one cosine curve and one constant. So you get this total. That means at delta equal to 0, if you find it, it will be actually E0 VT by XS minus VT square by XS. So VT by XS যদি common now, it will be VT by XS into E0 minus VT. Again, similar situation. Normal excitation E0 equal to VT, the resultant will be 0. That means the curve will pass from the origin. That means E0 equal to VT, the third plot shown, for both plus delta and minus delta. That means generating and motoring. Now E0 greater than VT overexcited, so it is something like the second one, right, which is having a positive value at delta equal to 0. So you get this one. And E0 less than VT underexcited, there is a fourth one where actually the resultant Q is negative at delta equal to 0. That means that one, bottom one. Okay. Now to calculate the maximum reactive power requirement, that means you have to dq delta 0. That means VT by XS cos time, if you differentiate with minus sign time, will be 0. So delta m will be actually pi. 0 actually is not cannot be taken because you see that at delta equal to 0, I mean there is no at delta equal to 0 if you put, so you get power, but actually it is not exactly the minimum one. So that is why you get oh, this one. You get at delta m equal to pi, and for plus pi it is for the generating, and for minus pi it is for the motoring. Okay. Now, if you put at delta equal to pi, maximum power you see, delta equal to pi, this is minus cos delta, minus cos pi is minus 1. That is minus E0 VT by XS minus VT square by XS. So you get actually the maximum value at delta equal to pi. So at delta equal to 0, it cannot happen because it is one value is positive, one value is negative. Although mathematically it is coming, but physically at delta equal to 0, you don't get the maximum magnitude of power. It gives you the minima actually. Always past derivative can give both minima and maxima. So if you put there, you can get d2q d delta. So you don't get that positive value. Okay, to get sorry, negative value to get maximum. So here in that way you get the maximum power, yes, and then maximum power you can put minus VT by XS into E0 plus VT, right? Same as that for generator. motor and generator maximum values are same, minus Vt by x is E0 plus Vt and minus Vt by x is E0 plus Vt, but one angle is plus pi, another angle is minus pi. Okay, so same way you can do it for Ra not equal to 0 and you can get the similar plot. Okay, so up to this I finished today, right? Up to this I finished today, and your term test will be up to this, page 13. So I will try to, you can consult the books also. I will be sending you the notes by today evening for this part. Okay. শুনতে পাচ্ছ? বই কনসাল্ট করবে এই পর্যন্ত সিলেবাস, ঠিক আছে? আর আমি নোটটা দেখছি আজ সন্ধ্যে বা কাল সকালে পাঠিয়ে দেবো। হ্যাঁ, by 19th, 18th, 19th, you may make it sure that you can give the class test or the intermediate assessment. Okay. আজকে কারা ছিলে? মাত্র 9 জন, তো অনেক ঢুকলো তারপর সব বেরিয়ে গেছে নাকি? রাহুল, তাহলে এরকম তো মুশকিল। আচ্ছা ঠিক আছে, ঠিক আছে, তাহলে মানডে টুইসডে করে একটা ক্লাস তাহলে আমাকে অ্যারেঞ্জ করে দাও নেক্সট উইকে। হ্যাঁ, মানডেটা ছুটি আছে, মানডে ভালো হয়, টুইসডে আই হ্যাভ টু গো টু দ্য ডিপার্টমেন্ট, দেন ওয়েন দিতে পারো না হলে। ওকে, তোমাদের ওয়েডনেসডে কি ফাঁকা পাওয়া যাবে? আচ্ছা, ডেট দেখে তোমরা আমাকে একটা বলবে, হ্যাঁ, নেক্সট উইকে একটা কোন ডেটে ক্লাস নেওয়া যায়, ঠিক আছে? ঠিক আছে, তোমাদের সঙ্গে তো আমার বোধহয়, হ্যাভ ইউ সিন মি অর হ্যাভ আই সিন ইউ? দেখা টাকা হয়েছে না? সেই ইয়েতে শুধু হয়েছিল না, কম্পিউটার সিপিএনএম এ? তো আমি তাহলে বেরিয়ে যাচ্ছি। ওকে, ওকে, হ্যাঁ, হ্যাঁ।